Hello and most welcome to 1162 of the series. We will continue with György Buzsaki. And now we left chapter 5 and gone to chapter 6. Brain rhythms provide a framework for neural networks. I'll just take away a little bit of the light here. Brain rhythms provide a framework for neural syntax. Rhythms imposes unanimity upon the divergent. Melody imposes continuity upon the disjointed. And harmony imposes compatibility upon the incongruous. György Buzsaki, the famous director. Language is a process of free creation. Its laws and principles are fixed, but the manner in which the principles of generation are used is free and infinitely varied. I would define in brief the poetry of words as a rhythmical creation of beauty. Edgar Allan Poe. I was mesmerized when, as a middle school student in Hungary, I first heard Morse code in ham radio course I attended, sending signals through the ether with a transmitter. The instructor told us that somebody from New Zealand had responded to his call. The operator on the other side of the world informed us about the sunny weather there and the receiving conditions, the details of his rig and the antenna he used. My surprise only increased. When I figured out that our instructor did not speak either English nor Maori, and presumably the operator in New Zealand did not understand Hungarian. Instead, I was informed they spoke to each other with dots, short pulses, and dashes, long pulses, through a universal language in which all words consist of 3 letters called Q code. To be a part of such a conversation, all I had to do was to learn Morse code, memorize the Q language, learn a bit about electronics, pass exams, get a license, build a transmitter and receiver, and set up a wire antenna between the chimneys of our house and the neighbors. Then I could communicate with any ham radio around the globe. That is exactly what I did, and the problem of coding has bugged me ever since. In learning Morse code, the biggest hurdle is to recognize letters in the sea of dots and dashes, separated by short spaces. Separation of messages is the most important thing in any coding system, be it speech, written language, computer language, or spike transmission in the brain. In Morse code, letters are separated by silent periods of the duration of a dot, whereas words have boundaries of at least 2 dots length. Similarly, if this entire page were a single long word, it would be very difficult to decipher the content, although not impossible, because unique combinations of 30 letters are much easier to decode than combinations of only 2 characters. The situation with neuronal messages is even more complicated because action potentials are all pretty much the same, just dots. Human language is also produced by combining elements. For instance, linking letters in a particular sequence produces words which have new qualities not present in the individual letters. Such combinations are regulated by syntax, a set of rules that govern the transformation and temporal progression of discrete elements, such as letters or musical notes, into ordered and hierarchical relations, words, phrases and sentences, or chords or chord progressions that allow the brain to interpret their meaning. Grouping or chunking the fundamentals by syntax allows the generation of virtually infinite numbers of combinations. From a finite number of lexical elements, using a minimum numbers of rules in music, human, sign, body, artificial, and computer languages, as well as in mathematical logic. With just 30 or so letters or sounds and approximately 40,000 words, we can effectively communicate the entire knowledge of humankind. This is an extraordinary combinatorial feat. Syntax is exploited in all systems where information is coded, transmitted, and decoded. In this chapter, I suggest that neural rhythms provide the necessary syntactical rules for the brain so that unbounded combinatorial information can be generated from spike patterns. A hierarchical system of brain rhythms, a framework for neural syntax. Researchers who study neural rhythms and oscillations have created an interdisciplinary platform that cuts across psychophysics, cognitive psychology, neuroscience, biophysics, computational modeling, and philosophy. Brain rhythms are important because they form a hierarchical system that offers a syntactical structure for the spike traffic within and across neural circuits at multiple timescales, and their alterations invariably lead to mental and neurological disease. The transmembrane potential of neurons can be measured by electrodes, which can report neural activity with sub-millisecond time resolution. Electric current flows from many neurons superimposed at a given location in the extracellular medium to generate a potential with respect to a reference site. We measure the difference between active and reference locations as voltage. When an electrode with a small tip is used to monitor the extracellular voltage contributed by hundreds to thousands of neurons, we refer to this signal as the local field potential, LFMP. Recordings known as the electrocardiogram, ECOG, are made with larger electrodes placed on the brain surface or its surrounding dura mater to sample many more neurons. Finally, when even larger footprint electrodes are placed on the scalp, we call the recorded signal an electroencephalogram, EEG for short. Each measure refers to the same underlying mechanism and neuron voltages, but because of the different sizes of the monitoring electrodes used in LFP and ECOG and EEG recordings, they integrate over increasingly larger numbers of neurons, from a few dozens to millions. The magnetic field induced by the SEM transmembrane activity of neurons is known as the magnetoencephalogram. The patterns measured by LFP, ECOG, EEG and MEG are very useful for the experimenter because they provide critical information about the timing of cooperating neurons. Like noise measured in a football stadium, these techniques cannot provide information about individual conversations, but can precisely determine the timing of potentially important events, such as a goal in the stadium or the emergence of a synchronized pattern in the brain. Monitoring LFPs or magnetic fields is the best available method for identifying brain state changes and faithfully tracking dynamic population patterns such as brain rhythms. A system of rhythms. There are numerous brain rhythms from approximately 0.02 to 600 cycles per second, covering more than 4 orders of temporal magnitude. Many of these discrete brain rhythms have been known for decades, but it was only recently recognized that these oscillation bands form a geometric progression on a linear frequency scale or a linear progression on a natural logarithmic scale, leading to a natural separation of at least 10 frequency bands. The neighboring bands have a roughly constant ratio of E 2.7, the base for the natural logarithm. Because of this non-integer relationship among the various brain rhythms, the different frequencies can never perfectly entrain each other. Instead, the interference they produce gives rise to metastability, a perpetual fluctuation between unstable and transiently stable states, like waves in the ocean. The constantly interfering network rhythms can never settle to a stable attractor, using the parlance of nonlinear dynamics. This explains the ever-changing landscape of the EEG. Traditionally, the frequency bands are denoted by Greek letters. Several rhythms can temporarily coexist in the same or different structures and interact with each other. Their constellation determines various brain states, such as stages of sleep and the arousal levels of waking. The different oscillations generated in cortical networks show a hierarchical relationship, often expressed by cross-frequency phase modulation between the various rhythms. This term implies that the phase of a slow oscillation modulates the amplitude of a faster rhythm, meaning that its amplitude varies predictably with each cycle. In turn, the phase of the faster rhythm modulates the amplitude of an even faster one. This hierarchical mechanism is not unique to the brain. Spring, summer, fall and winter are 4 phases of a year that modulate both the amplitude and duration of day length. In turn, the phases of the day are correlated, i.e. phase-locked, with the alignment of the sun and moon, which modulate the tidal magnitude of the oceans. Because of cross-frequency coupling, the duration of the faster event is limited by the allowable phase extent of the slower event. The fastest oscillation is phase-locked to the spikes of the local neurons, and because of cross-frequency, Because of cross-frequency coupling, the duration of the faster event is limited by the allowable phase extent of the slower event. The fastest oscillation is phase-locked to the spikes of the local neurons, and because of cross-frequency coupling to all slower rhythms of the hierarchy. For example, the ultra-fast oscillatory ripple waves in the hippocampus are phase-locked to the spikes of both pyramidal cells and several types of inhibitory interneurons. And the magnitude of the short duration ripple events, approximately 40 to 80 milliseconds, is modulated by the phase of the thalamocortical sleep spindles. The spindle events in turn are phase modulated by cortical delta oscillations, which are nested in the brain-wide infraslow oscillations. The nested nature of brain rhythms may represent the needed structure for syntactical rules, allowing both for the separation of messages and the linking into neural words and sentences. Punctuation by inhibition. The excitatory pyramidal neurons are considered to be the main carriers of information in the cortex. Their potential runaway excitation is curtailed by inhibitory interneurons. The 15 to 20% of cortical neurons that contain the inhibitory neurotransmitter gamma aminobutyric acid, the GABA. The main function of these neurons is to coordinate the flow of excitation of neuronal networks. There are several different classes of inhibitory interneurons with specialized functions. One group selectively innervates the axon's initial segment of pyramidal cells, where the action potential is produced and can influence the timing of spikes. A second group innervates the region surrounding the cell body and can electrically segregate the dendrites from the axon. A third group is dedicated to dendritic inhibition. The main function is to attenuate or filter out excitatory inputs onto different dendritic segments. Dendritic targeting interneurons can also effectively short-circuit entire dendritic branches or trees, thus dynamically alter the biophysical properties of the inhibited principal neurons. Yet another group exclusively inhibits other interneurons. Interneurons collect excitatory inputs from the surrounding pyramidal cells and respond equally effectively to distant excitatory neurons or to subcortical neurons carrying various neuromodulators. In turn, the axons of most interneurons arborize locally, providing inhibition to the surrounding pyramidal cell population. Finally, a smaller important group of inhibitory cells project their axons to distant structures, hence the name long-range interneurons. Although there is no agreed job description for each of these interneuron types, their overall task is akin to traffic controllers in a big city. The ability to stop or slow excitation and route the excitatory traffic in the desired direction is an important requirement in complex networks. To be effective, the various traffic controllers should be temporally well coordinated for each given job. Inhibition of the excitatory neurons can be conceived as the punctuation marks of a neural syntax that can parse and segregate neuronal messages. The segregating or gating effect of neural oscillations can be illustrated by considering a single neuron whose membrane potential is fluctuating around the action potential threshold. The outcome of afferent excitation of a neuron depends on the state of the neuron. If the membrane potential is close to the threshold, a very small amount of excitation is enough to discharge the cell. However, when afferent excitation arrives at the time of hyperpolarization, the input may be ignored because axons of the interneurons target many principal cells. Inhibition can effectively synchronize the action of the principal cells. If the discharge of interneurons is temporally coordinated, for example by oscillatory mechanisms, many pyramidal cells in the network can produce synchronous output and exert a stronger effect on the downstream targets compared with a non-coordinated or asynchronous firing. In some, the concerted action of interneurons can route the excitatory information at the right time and in the right direction. Inhibition creates oscillations. Inhibition is the foundation of brain rhythms, and every known neural oscillator has an inhibitory component. Balance between opposing forces, such as excitation and inhibition, can be achieved most efficiently through oscillations. The output phase allows the transmissions of excitatory messages, which are then gated by a build-up of inhibition. Oscillations are energetically the cheapest way to synchronize the constituents of any system, be it mechanical or biological. This may be a good reason for brain networks to generate oscillations spontaneously when no useful external timing signals are available. Inhibitory interneurons can act on many target neurons synchronously, effectively creating windows of opportunity for afferent inputs to affect inhibition-coordinated local circuits. In summary, oscillatory timing can transform both interconnected and unconnected principal cell groups into transient coalitions, thus providing flexibility and economical use of spikes. Brain-wide coordination of activity by oscillations. In contrast to computers, where communication is equally fast between neighbors and physically distant components, acts and conduction delays in the brain limit of the recruitment of neurons into a fast oscillatory cycles. As a result, infra-slow waves are of tsunami size, involving many neurons in large brain areas, whereas superfast oscillations are just ripples riding on the vortex of the slower waves and contribute mostly to local integration. The consequence of such cross-frequency relationships is that perturbations at slow frequencies inevitably affect all nested oscillations. An important utility of cross-frequency phase coupling of rhythms is that the brain can integrate many distributed local processes into globally ordered states. Local computations and the flow of multiple signals to downstream reader mechanisms can be brought under the control of more global brain activity, a mechanism usually referred to in cognitive sciences as executive, attentional, contextual, or top-down control. These terms reflect the tacit recognition that sensory inputs alone are not enough to account for the variability of network activity, so some other sources of drive must be assumed. These other sources can be conceived of as a supervising signal coming from pre-existing wiring and the brain's knowledge base, which can provide a necessary grounding for the meaning of sensory input. Global coordination of local computations in multiple brain areas through cross-frequencies coupling can ensure that information from numerous areas is delivered within the integration time window of downstream reader mechanisms. A useful analogy here is the cocktail party problem. When many people speak at the same time, comprehending a conversation is much easier when the listener can also see the actions of the speaker. Movements of the lips and facial muscles involved in speech production precede the sound by several tenths of milliseconds, and the patterns are characteristically correlated with the uttered sounds. Thus, visual perception of the sound production information can prepare and enhance sound perception. Visual information reaches the auditory areas of the brain just in time to be combined with the arriving auditory input. Indeed, watching a silent movie with human speakers activates auditory areas in the listener's brain. Understanding someone with a foreign accent is difficult initially, but the listener can catch up quickly by combining auditory and visual information. A temporal discrepancy between acoustic and visual streams may introduce comprehension difficulties, but people quickly learn to compensate for it. Input-output coordination. Neural oscillations have a dual function in neuronal networks. They influence both input and output neurons. Within oscillatory waves, there are times when responsiveness to stimulus is enhanced or suppressed. We call them ideal and bad phases. Oscillation is an energy-efficient solution for periodically elevating the membrane potential close to the threshold, thus providing discrete windows of opportunity for the neuron to respond. The physiological explanation for this gating effect is that the bad phase of the oscillatory waves is dominated by inhibition. As discussed earlier, whereas excitation prevails at the ideal phase. The same principle applies at the network level. When inputs arrive at the ideal phase of the oscillation, that is, at times when neurons fire synchronously and thus send messages, they are much less effective compared to the same input arriving during the bad phase of the oscillator, when most neurons are silent. As discussed earlier, activation of inhibitory interneurons can hyperpolarize many principal neurons simultaneously. Recruitment of inhibitory interneurons can happen via either afferent inputs, feed forward, or via pyramidal neurons of the activated local circuit feedback. As a result, the same mechanism that gates the impact of input excitation also affect the timing of output spikes in many neurons in the local circuit. Such synchronized cell assembly activity can have a much larger impact on downstream partners. Such synchronized cell assembly activity can have a much larger impact on downstream partners than on individual uncoordinated neurons with irregular interspike intervals. This dual function of neuronal oscillations is what makes them a useful mechanism for chunking information into packages of various lengths. Brain rhythms across species. The brain is among the most sophisticated, scalable architectures in nature. Scalability is a property that allows a system to grow while performing the same computations, often with increased efficiency. In scalable architectures, certain key aspects of the system should be conserved to maintain the desired function, while other aspects compensate for such conservation. Temporal organization of neural activity, as represented by rhythms, is a fundamental constraint that needs to be preserved when scaling brain size. Indeed, perhaps the most remarkable aspect of brain rhythms is their evolutionary conserved nature. Every known pattern of LFPs, oscillatory or intermittent, in one mammalian species is also found in virtually all other mammals investigated to date. Not only the frequency bands, but also the temporal aspects of oscillatory activity, such as duration and temporal evolution, and importantly, their cross-frequency coupling relationships and behavior correlations are also conserved. For example, the frequency, duration, and waveform. And cortical localization of sleep spindles are very similar in the mouse and in the human brain. On the one hand, this may not be so surprising. After all, neurotransmitters, their receptors, and the membrane time constants of principal cells and interneurons are also conserved, and these properties underlie various oscillations. Thus, irrespective of brain size, the management of multiple timescales in neuronal networks is supported by the same fundamental mechanisms. On the other hand, the speed of communication between areas varies considerably between small and large brains, making the conservation of rhythms unexpected. For example, the coherent perception of multimodal inputs, the results of local computation in the thalamus, and several primary sensory cortical areas should arrive within the integration time window of the target associational cortices. The same applies to the motor side of the brain. As discussed in Chapter 3, the fundamental properties of myosin and actin are largely conserved across mammals. Therefore, the motor command computations in the motor cortex, the cerebellum, and basal ganglia should be performed in should be performed in comparable time windows. The command signals to the spinal cord should be delivered within the same time range in different species. However, the distances of these structures vary by orders of magnitude across species. Thus, all of the timing constraints required for adequate function have to be reconciled with the complexity imposed by the growing size of the brain. This is not a trivial task, given a 7,000-fold increase of brain volume from the small tree shrew to the large brain cetaceans. The constancy of the main brain oscillations and their cross-frequency coupling effects across species suggests a fundamental role for temporal coordination of neuronal activity. Conservation of brain rhythms across species. There appear to be at least two mechanisms that allow scaling of neuronal networks while conserving timing mechanisms. The first mechanism compensates for the increase in neuronal numbers and the enormous numbers of possible connections by shortening the synaptic path length between neurons, defined as the average number of monosynaptic connections in the shortest path between two neurons. This problem is akin to connecting cities with highways and airlines to obtain an efficient compromise between the length of the connections and the number of intermediate cities required to get from city A to city B. Directly connecting everything with everything else is not an option in most real-world networks, as the number of connections increases much more rapidly than the number of nodes to be connected. An efficient compromise can be achieved by inserting a smallish number of long-range shortcut connection into local connection. The resulting small world-like architectural solution allows for scaling while keeping the average synaptic path length similar as the brain increases in size. While such scaling prevents excessive volume growth, longer axons increase the travel time of action potentials. This would pose a serious problem for neural communication. Thus, a second mechanism is needed to compensate for these time delays. This requirement is solved by using a larger caliber, better insulated, and more rapidly conducting axons in more complex brains. For example, to achieve interhemispheric gamma band synchrony in the mouse brain, a conduction velocity of 5 meters per second is sufficient. On the other hand, maintaining coherent oscillations in the same frequency range in the human brain with 70 to 160 millimeters between hemispheres requires much more rapidly conducting axons. Thus, the benefits of timing mechanisms in larger brains can be preserved by adding larger caliber and more strongly myelinated axons that allow signals to travel longer distances within a similar time window. In the human brain, the great majority of interhemispheric, that is callosal axons, have small diameters, but the thickest 0.1% can exceed 10 micromillimeters in diameter. This thick fibers scale best with brain size, whereas the fraction of thinner fibers actually decreases. Although adding some large diameter axons does increase brain volume and metabolic costs, the resulting volume increase is still considerably smaller than would result from a proportional increase in axon caliber across all neurons. This small added fraction of large diameter axons can be responsible for the minor variability of interhemispheric conduction delays across species. Although the exact neuron types with large caliber axons are not known, experimental data indicate that at least some of them originate from long-range inhibitory neurons. In turn, theoretical considerations and modeling suggest that long-range interneurons are critical for brain-wide synchronization of gamma and potentially other oscillations. In summary, preservation of brain rhythms in increasingly larger brains can be taken as supporting evidence for the fundamental importance of timing in brain performance. It is clear that oscillations per se do not serve special biological functions. The meaning of gamma oscillations in the sensory olfactory bulb is different from those in prefrontal circuits serving cognitive functions. Instead, the benefits of particular oscillation depends on the function of the brain system that supports it. Entrainment of oscillators, tracking temporal dynamics of speech. When two oscillators with identical frequency engage each other, the outcome depends on the phase of the two rhythms. In phase interactions, induced resonance. In phase interactions induce resonance and as a result amplification. In contrast, opposing phase interactions may annihilate or dampen the rhythm. In contrast, opposing phase interactions may annihilate or dampen the rhythm. Oscillators with non-integral relationships induce perpetual interference. This is typical of brain rhythms, and the interference mechanisms explain why brain dynamics is constantly changing, similar to the interference of ocean waves. or why not the wave-particle duality, which plays a role here as well, and much important. Occasionally, the oscillatory reader mechanism may transiently adjust its phase to the incoming inputs. Such phase adjustment is among the most important flexible features of brain oscillators. This is similar to how musicians in an orchestra keep the beat. If the first violist is a bit faster, the rest of the musicians adjust the timing of their movements. Furthermore, the phase separation of the maximum and minimum spiking activity of the information transmitting principal cells make oscillators a natural passing mechanism. As mentioned earlier, this is an effective separating mechanism of neural messages. A fundamental requirement for syntactical operations. Speech rhythms are brain rhythms. A striking example of the selection and amplifying properties of brain oscillators is their response to speech. Rhythms of human speech are remarkably similar. Across all spoken languages, and our brains are tuned to efficiently track and extract such information. We can easily recognize a stutterer, or a person with a speech impairment in any language because of the altered speech rhythm. The so-called prosodic features of speech, such as intonation, stress and pause, are characteristic of individuals. Yet they also share common features among all people, varying between 0.3 seconds and 0.2 seconds, the delta band. Syllables also repeat somewhat rhythmically between 4 and 8 times per second, while phonemes and fast transition are characterized by a frequency band between 30 seconds and 8 through second gamma band. Two features of brain oscillations can facilitate the extraction of hierarchically organized continuous speech. First is the correspondence between speech and native brain rhythm frequencies. The cross-frequency phase coupling can amplify sound features and assist with the segmentation of speech components. Second, the ability of neural oscillators to reset their phase can effectively track the temporal features of quasi-rhythmic spoken language. It is tempting to draw a parallel between neural syntax, supported by brain rhythms, and language syntax. Brain rhythms may constrain the way our motor system controls utterance of sound. In return, the phonetical syntax of speech referring to the sequences of sounds, can influence brain oscillations. I make this comparison later with the explicit acknowledgement that there is a difference between speech syntax and syntactic coding of speech. Yet the brain-constructed and human community-constructed syntactic rules often seem correlated. Wow! Experiments using EEG and make methods have demonstrated that the edges of the sound envelope of speech can reset the phase of slow brain oscillations in the right temporal and frontal areas, and that speech sound envelope fluctuations are correlated with amplitude variations in the delta band. The time-varying dynamics of syllable sequences can be faithfully tracked by the amplitude of theta oscillations and the integrated amplitude of gamma activity. In high-density ECOG recordings from the surface of the superior temporal gyrus,